Here's number 12. All right.
Hey, you want to do it with my number?
No.
I did it twice.
You can do it with my numbers. I
I
did
did
it
it both times.
You have to answer. And it was right.
It is.
Okay, here we go.
MB.
All right, in this particular problem, you have a bullet moving at V naught. I'm going to have the bullet being mass of little b since it's small, and the mass of the block being mass of big B. Okay? And the bullet hits the block, and I think it asks what's the maximum height the block goes, correct?
Yeah. No.
Yeah, that's
The
the initial velocity
is
of the bullet.
And oh, with the initial velocity of the bullet, so does it tell you how high the block goes?
Yeah.
Yes. Like
Okay.
1-2 meters.
Oh, okay.
In her case.
So it goes a height of h. Nice try. All right, so it goes a height of h. But wait a minute, when it's up here, is it just the block, or what kind of collision was it?
It's
It's
a
a inelastic.
Completely inelastic, so it's stuck, right? So the bullet entered the object and stuck inside there, right? All right, so, okay. Anything else I need to know, or is that it?
it looks like
Is that it? All right, now, here we go. What kind of physics? How many different distinct spots do we have? Does that have B and W? Which one is W? Oh, okay, so you want to do W and B. All right, that'll work. We can do W and B, so that's wood and block. So that, therefore we don't get too confused with our, I'm sorry, wood and bullet. So we don't get too confused with our two B's here. All right? How many distinct, different regions do we have in this problem? We have, oh, and it's now you're already connecting them. Okay, so tell me this then. If you're going to do it that way, that's fine. How many different physics things go on here? What different types of physics are occurring here?
conservation.
Conservation of energy?
Momentum.
Right?
Okay, which one is it? Conservation of energy or momentum?
Oh, yeah.
Oh, we have both?
No.
Where's conservation of energy?
Well, you know, in the kinetics, you go to potential.
Oh, so from here to here,
Yeah, the potential.
from here to here, I'm going to call this, well, okay, whatever, from here to here. I was going to call this location 2 when they get hit. So what we really have is this, bullet before it hits, and then you have
Bullet winning.
bullet when it hits, and then you have bullet and block after it hits and goes to its maximum height. Is that right?
Yeah.
So 1, 2, 3. So you're saying that the conservation of energy is the connection between which locations? 1 and 3?
Wait, no, 2 and 3.
2 and 3.
When it,
It is, yeah.
Okay, the connector between these two is conservation of energy. Energy at 2 equals energy at 3. Why can I not say energy at 1 equals energy at 3?
You have
What?
velocity.
What keeps us from doing that?
Because energy at 2 is all kinetic, right? Because it's moving. And energy at 3, it's at max height, so technically its velocity is 0, so there's no kinetic energy.
So the energy here is kinetic energy, and the energy here is gravitational potential.
And
But don't I have kinetic energy here?
gravitational potential just for the wood.
but it's not, and
The
it's
bullet.
and it's not moving.
Okay, here's our key. Say it loudly again.
Since it's an inelastic collision, kinetic energy is infinite.
Okay. Between here and here, what kind of collision? Completely inelastic. So is kinetic energy conserved? We're going to lose some kinetic energy. What do we lose it to? Yeah, heat, sound, something that we are not able to keep track of. Now, if we are able to keep track of, like say we say that the bullet enters the block and generates heat. If we can make that assumption, then we could say that the energy here equals the energy here equals the energy here. We would have the original kinetic energy of the bullet here. We would have the, all of that energy, some of that kinetic energy is turned into this kinetic energy, but not all of it, right? Some of it is lost to heat, right? And then this kinetic energy here equals this potential energy here. Here's the deal, is we don't have a good way of figuring out how much heat is generated, right? Unless we just assume the kinetic energy that's lost all turns into heat, right? So we can really only easily say that the mechanical energy, anyway, is conserved from here to here. The mechanical energy is not conserved from here to here because we lose some of our mechanical energy, kinetic and potential, to heat somewhere in this region, right? Okay. So kinetic energy is conserved here. So who was saying that we have conservation of potential? Conservation of momentum. Conservation of momentum. Conservation of momentum. Who was our vote for that?
That was you, Chris, wasn't it?
Oh, that was me.
Oh yeah, conservation of momentum. Why? Oh, why?
Why are you so white?
Because between here and here we have a collision. And anytime we have a collision, can we keep track of all the objects colliding? Yes. Are there any other outside forces going on that influence the collision between here and here?
Not in our world.
Yeah, there's gravity, but as long as the collision takes place over a short period of time where it's not really lifting off the ground much, then we can neglect that, right? There is friction, but the friction is between the bullet and the block, and so that becomes an internal force of our two objects, right? So we don't care. So we have conservation of momentum from here to here, conservation of energy from here to here. What are we trying to find? That velocity, right? Since we're trying to find that velocity, let's just write this equation and write this equation and see where it takes us, okay? So what's our momentum equation going to be?
P1 equals P2 first, right?
P1 equals P2.
So M1.
M for which one?
MB.
The bullet.
V sub O.
V sub O.
Equals plus MW.
MW.
Zero, essentially, so you can cross that.
Okay, but the velocity of the wood at the beginning is 0, so we could have just neglected it, right?
Equal to
MV plus MW times the velocity. I'm going to call it velocity 2 because that's the velocity it takes off with. Okay? All right, so how many of these things do we know? We know M, we know our M's, right? And this we can get rid of, so we can erase that. So unfortunately we have two unknowns, that one, which we're looking for, and that one. So we cannot solve that. There's nothing wrong with that equation, we just can't do anything with it yet, right? Okay, so let's move on over here. Energy. Energy at 2, what kind of energy? Kinetic only, right? Because the thing is moving, and we're going to call this our height equals 0. What kind of energy do we have up here?
Potential.
Just potential, gravitational potential, right? And that is at a height of h, right? So this becomes 1/2 mv2 squared equals mgh. Now I didn't even bother putting in what the masses are. Technically I should have put in this mass plus this mass, right? But does it matter? No, because it crosses out. So now I end up with 1/2 v2 squared equals gh. All right, what do I know here? I know g, and I know h, and I know my 1/2, and hey, so I can solve for this. Then what do? Plug it in there, and then I solve for that. Very nice. Ooh, okay, if you've got grams and kilograms in this problem, which should we convert?
Kilograms.
You need to convert 2 kilograms, correct?
2 kilograms, yes.
Because otherwise we're going to get, well, I guess right here it won't matter, but since this is going to be in meters per second, we're going to need to Actually, you know what? It doesn't matter because you're going to have you're going to have either kilograms and kilograms, or you're going to have grams and grams. They'll cancel out. It won't matter.
So as long as you just convert them to the same one.
As long as you have the same unit in this case, you'll be okay. All right, so there's number 12. We okay with that one? All right. Now, this particular problem is very similar to the problem in your review packet that looks like this, where you've got this block hanging from the ceiling and you shoot a bullet into it. And you shoot the bullet into the block, and then the block swings upward.
Oh, the swinging thing was this.
Lab, we should go to the gun.
Swings up like that. All right? That is in our packet. It is Problemo 185. Okay? Now, this one right here. Between here and here, what's the connector? What kind of physics describes the bullet hitting the block? It's collision, therefore it's probably going to be conservation of momentum. So,
We're on the packet.
we're in the packet.
Are you going to do number 13?
I will do number 13 in a minute.
This is something special. What number is it?
This is problem 185 in our review packet. Okay, look at this. This is almost identical to that one.
Oh, sure.
Bullet hits block. What's the physics that describes this?
Conservation of
Conservation of momentum.
and conservation of energy up there.
And then from here to here, it swings upward this time.
With no air resistance.
No air resistance. So again, we have kinetic energy here turns into gravitational potential energy up here. And those must be equal, right? From this location to this location. So 1, 2, 3. The connector from 1 to 2 is momentum. Connector from 2 to 3 is energy. Okay? Where you have a table and you have a sphere here and a sphere here. This one's moving along, and when they hit, this one takes off and lands down here on a table. All right? From here to here, what kind of physics?
Collision.
It's a collision. So right here we have conservation of momentum. From here down to here, what kind of physics? It looks like trajectory motion, 2D kinematics.
It's a Rudy Catalina problem.
It's a Rudy Catalina problem. All right, let's go to our next one. The one with the spring, problem 283. Problem 283 looks like this. You've got a block moving along to the right with a velocity, and another block attached to a spring. So this one moves along, hits this one. After it hits it, they compress, they stick together and compress the spring. Okay, this part right here where they hit and collide, what kind of physics?
Collision.
It's a collision. Therefore, probably conservation of momentum.
Yay.
P1 equals P2. But then after they collide, stick, and move backwards, what kind of physics is that?
Like spring potential.
Okay, what about springs? Because we could do forces with springs, we could do energy with springs.
Energy. Well,
Yeah, if you got a choice, which one's easier?
energy.
Energy, right? So let's try energy. What kind of energy will these two blocks have when they start to move backwards?
Potential will increase.
Potential's going up at the expense of
Kinetic.
kinetic. So we're starting with kinetic energy of the blocks, and that's going to turn into spring potential, right? All right. Now, this is different than the stuff we did last year. Last year, all the stuff we did was always, it was either momentum or energy, right? But now we're using several different types of ideas. Yeah, momentum and trajectory motion, momentum and energy, things like that, okay? So, that's the way our problems are going to be on our exam as well. Okay, so you have to tie them all together. Okay, which brings us to the real question, which was e-homework number 13, which looks somewhat evil.
E5.
Evil.
Is it equal?
Okay, it looks like this. You have a cue ball coming along towards the 8 ball here, moving along at a velocity. Okay? Do they give you the mass of the two objects?
And just the same mass.
Okay, the mass is the same. We'll just call it M. Mass of the cue ball equals the mass of the 8 ball. That's all we know. All right? And then afterwards, after the collision, the cue ball takes off this way with a new velocity. We'll call this velocity 1 and 2 for the cue ball. So 1c and 2c. Okay? And then the 8 ball, oops, that's a pretty big 8 ball. Then the 8 ball takes off this way with its own velocity. I'll call that velocity 2 for the 8 ball, velocity 28. And then they give you a couple of crazy measures. They give you this measure, which is phi, and this measure, which is theta. All right? Now, this is a collision, right? It says, assume an elastic collision.
Why this?
All right? Cue ball is spelled with a C. C-U-E, right?
With CUE.
You spell it with a Q? Oh. All right. Q-U-E.
It's a
Dang.
different kind.
My-
It's like I'm.
That's like
I'll
saying.
give you the cue, and when you go on stage.
Yes,
That's
that's
CUE. CUE is the one I'll give you a Q.
Because I thought cue ball was spelled with a C, wasn't it? It's C-U-E, isn't it?
No, here on it's the QUE.
It's a retarded.
But in here they call it the Q-U-E-U-E, which is Q is like you start your line on cue, like in a play, right? What kind of physics does it look like?
Collision.
Looks like collision, but whoa, it's not like this kind of collision.
It's 2D.
It's a 2D. So that means that in the x direction,
There's an original momentum.
the momentum of the cue ball originally plus the momentum of the 8 ball originally, oops, I'm doing them backwards. I did 1, didn't I?
Yeah.
Must equal, in the x direction, must equal the momentum afterwards of the cue ball in the x direction plus the momentum of the 8 ball afterwards in the x direction. Yikes, that looks really complicated. But wait, this one's 0. Correct? Okay. So we know that this momentum right here, this x momentum here, and this x momentum here,
Add up.
those must add up to be this one, right? Okay. And everybody, there's another kind of cool thing here. The mass times the original velocity of the cue ball must equal the mass times the velocity 2c in the x direction plus the mass times velocity 2,8 in the x direction. Everybody following me so far? But what about all the n's? Hey, they're all the same. All right? So velocity 1c equals velocity 2c in the x direction. Yeah, it's a c. But can we simplify that a little bit? The velocity in the x direction here, that's just going to be velocity of 2c times cosine of theta, right? Is everybody okay with that? Plus the velocity 2,8 cosine of phi. All right, so what ones do we know? We know that one,
We know V2C,
and we know that one.
that's it.
And we've got unknown here, here,
And then,
and
Are
here.
you kidding me?
3 unknowns.
so we do it the other way.
Ah! So let's try the y direction and see what it says. In the y direction, why is the momentum in the y direction going to be a little easier?
It starts off with 0.
Hey, because we start off with 0. So when I say momentum 1 in the y direction equals momentum 2 in the y direction, that's 0. And then what do I have? I've got a y momentum here,
So V2C.
and I got a y momentum here, and those two must cancel. So they must be equal. So I'm just going to do this. Instead of putting 0 equals 1 minus the other, I'm just going to say that they're equals. Is everybody okay with that?
Yeah.
Okay, so that's going to be m v2c in the y direction must equal m v28 in the y direction. Does that make sense? Because it's the mass times velocity. This is my final velocity, and I want the y component and the y component here.
But mass is still.
But the masses go away again, because the mass is the same. And I can make this to be V2C times the sine of theta, is that right? Equals V28 sine of phi. Is everybody okay with that?
But we still.
Okay, what do we know?
We know V2C, the rest are other.
We know that. And question mark, question mark, question mark.
This is really turning into.
This is turning into something that we don't want to deal with, probably.
Yeah.
Why are we still stuck?
I'm gonna just play ping pong.
Mathematically, why are we still stuck?
Because we have no answer in one of the magnitudes.
Yeah, because the deal is we how many equations do we have? How many unknowns do we have?
Say.
We need a third equation.
Well, that's just.
What's our third equation?
I don't know about that. Conservation rate.
What kind of collision is it?
Elastic.
It's elastic. What does elastic collision mean?
Oh,
Energy.
Kinetic energy in 1 equals kinetic energy 2. Ooh, so how much kinetic energy do I start with?
1
1/2 mv1c squared. How much energy do I end with? 1/2 mv2c squared. Now, do I have to worry about the angles for kinetic energy?
No.
No, because it is a scalar, right?
Ah oui.
Energy is energy is energy no matter what direction. So we have another one, 1/2 mv28 squared. Oh, and all kinds of great magic occurs here. Oh yes, serious magic.
1/2 mass goes.
1/2 mass goes away. Look what I'm left with. V1c squared equals V2c squared plus V28 squared.
Oh, that's a, I thought that was a K the whole time.
But that was a what?
K.
A K? That's a 1c. All right, hey, whoa, whoa, what do we know? Do we know this?
Yeah. And
Do we know this?
So we know the.
Hey, whoa, do we need these two? What are we looking for?
Just
We're looking for this. And there it is. Wow. Hey, is this a momentum problem? Well, yeah, it is, but did we really use momentum? Only because we knew it was an elastic collision, we had this third equation. Okay? Now look, if you have objects that bounce off of each other like we had here, they are going to have to give you a little extra information because you cannot just solve it with these two. The extra information this time came from the fact that it was elastic. But if it was inelastic, if it was inelastic collision, then you couldn't have this one. So they would have to give you either the final velocity or they'd have to give you one of these angles. Because otherwise you can't solve it. It's
Well, if it-
impossible. to solve, because you'd have 2 equations and 3 unknowns. Okay? Or lots of unknowns. More than you have equations for. Okay, so our trick in this one is the fact that it is conservation, or that it is an elastic collision, which allows us to solve for our velocity directly. Otherwise, it would be much more challenging. It was challenging enough as it was because we didn't know where to go with this at the beginning, right?
Good, I like that.
Excellent. Turn to the very back page of your review packet. I want you to work the problem on the very back. Work it together. Make sure you all have the same answer. Actually, what I want you to work is parts A and B first. We'll talk about those, and we'll work C, D, and E. All right, so here we go. Has anybody figured out how to do this yet? Okay. How are you attempting to do it? What does it look like? It looks like momentum.
But it should be impulse moment.
It looks like this. Now, there is this mysterious graph floating around.
Hint, hint.
Yeah, a nudge, nudge, wink, wink, look at me graph. Okay? Now, let's just do this, because I want to show you how to do this on an exam. You're on an exam, and you're looking at this, and you go, hey, I got objects colliding. That is obviously momentum. So you start right here, and you say, look, how many objects do I start with? 2. How many are moving? Only 1. So I've got mv for the first one, and then afterwards I've got 2 objects. And I know that one's going to be moving, but this one,
Not sure.
I don't know. So it looks like it's going to be a problem like this. I know this mass. I know this velocity. So I'm going to end up with 6 kilogram meters per second on the left. On the right, I'm going to have 2 times a mystery velocity for this one, plus a mystery mass times 1.6. So I've got 2v plus 1.6 m. Okay, whoa, what's the problem here?
I don't know.
Yeah, I got 2 variables in 1 equation, so that's a problem. So a lot of you are thinking, okay, wait. Well, I'm just going to assume that this one stops. Now, you can assume that, but you have no reason to really assume that. You don't know. And if you don't know, you don't know. You got to find another way to look at it. Okay, so is there anything wrong with what we've done? No, we just can't get there where we want to go. Because we're trying to find that and that. Because it asks for both of them. Okay, what other information do we have? We have the graph. Whoa, look at this graph. Look at this pretty graph here. FT graph. What's FT graph tell you? It gives you the impulse. How do you find the impulse for an FT graph? Ah, this area.
That's our equation.
So the impulse equals the area. Can you see that yellow? The impulse equals the area. All right? Okay, now, danger, danger, caution, caution. Area. Look at your graph.
Units cancel out.
Oh, yeah, we luck out. If you didn't pay attention to your units, technically this is 10 kilonewtons. 10 times 10 to the third newtons. And this is 1 millisecond. 1 times 10 to the negative third seconds. Now, if you had not paid attention to that, you would have lucked out, and it wouldn't have mattered, because 10 times 1 is the same as 10 to the third times 10 to the negative third, right? Okay, you end up with the same answer. Okay, but to find our area, what's our area of that?
5.
It is
Newton
5
second.
what?
Newton second.
Newton seconds. Okay, now that's the impulse. What do I do with that?
Divide by mass to get
This equals
M
the
delta,
change in momentum,
which is equal to M delta.
which is equal to m delta v, because our mass is staying the same. So which mass do you want to mess with?
The 2 kilograms. That's what it's asking for.
You want to do the 2 kilogram one? All right.
That's the one it's
So
asking
we put the 2 kilogram one in here. 5 Newton seconds equals 2 kilograms times delta V. Now delta V literally means V final minus V initial. So there's my V final minus my initial of 3. So when I solve this, what is my final velocity? 5.5 meters per second.
It can go faster.
Well, wait a minute. If it was going to be going this way,
Gotta be going there.
how would this number tell you to the left?
Negative.
It'd be negative. It says positive.
But we have,
maybe they-
and we're defining that way positive, so.
We've defined this way as positive. Our answer is positive, so that must be to the right. Whoa, what's our problem?
They-
You
they-
can't
it's
set
like-
up
it's
and
like-
get to the same direction. Because it's wrong.
Why is it wrong?
You can't increase the speed to the same direction.
First of all, if this is you running down the hallway and you run into somebody else, do you speed up?
No.
Not in the direction you're going. And here's another dead giveaway that we got a problem. If that's 5.5 after the collision, it must have gone through this object. And do you see that I would have gained kinetic energy? Because this thing has sped up while speeding that one up, and so we've magically gained energy. Oh my goodness. We have a problem.
That force graph is on the other part.
Say it again.
The force graph is the force on the other part.
Okay, this force graph is for the force in general. But when this cart hits this cart, which way is the force on this cart?
The other way.
How do I represent a force this way on that cart?
You just flip the inverse.
Yeah, the graph is like this, right?
So it's a negative A.
It's a negative 5 because my impulse is in the negative direction. Ooh, now I cannot tell you how many times if I put this on a test, students will come up with 5.5. Actually, what happens is students get to here and they assume the velocity here is 0 because they don't know what to do. They get stuck, okay? So just remember, when you get to something here and you haven't made a mistake, you look at it and go, that's right. They just back up and say, is there another way? Is there some other information I have? And here's our information. And then when you look at this one, you go, that doesn't make any sense. Because it's positive, which means to the right. But it can't speed up. So what could we have done wrong? Well, the thing is that our impulse is a negative impulse. This one gets a positive 5. The impulse over here, I should put these as impulse. The impulses are equal but opposite. This one gets a negative 5, this one gets a 5 Newton seconds. So that one speeds up and this one slows down. So when I put in negative 5, what's my new answer?
0.0.
Is it 0.5?
0.0, yeah. 0.0. 0.5. 0.
Is that right?
Yeah.
Yes.
Okay. Now does that make sense?
Yes.
Okay, at least that makes good common sense. It's slowed down. It hasn't gone past the other one, right? Because that,
More fluid.
you know. All right, so if this velocity here now is 0.5 meters per second, this physics here that we figured out is great. That's now 0.5, and now we can find the mass of the other cart with conservation of momentum. 3.125 kilograms. There you go. Does that sound right, everybody?
I solved the mass first, and use that to solve the velocity.
This is a deceptively hard problem. This will be a strenuous test, but not anything beyond your ability. You can do it. But we got to go back and we got to talk about the other part of this test, not just momentum, Kinematics is on this test big time as well. Trajectory motion, and like the bottom part of this problem.
Kinematics is trajectory.
Separating.
It's like, yeah, kinematics is the study of motion. So in one-dimensional motion, you have those three equations, right? And then you have all the graphical things about kinematics, displacement, velocity, acceleration graphs, and then you have the trajectory motion stuff. Okay? All right. So here we go, everybody. Ready?
Yep.
Second part of the problem says, after the collision, the second cart eventually experiences a ramp.
That's a stupid way to word it.
Yeah, you'll see why they word it that way in just a second. Which it traverses with no frictional losses, so no friction. The graph below, or to the right, shows the speed v of the second cart as a function of time for the next 5 seconds, where t equals 0 is now the instant at which the carts separate. So the carts collide. After the collision, there's our velocity versus time graph. Okay, now we're into the realm of kinematics, which is talking about what's its motion like, displacement, velocity, and acceleration. So it says, calculate the acceleration of the cart, calculate the distance it's traveled, and state whether the ramp goes up or down, and calculate the maximum elevation. Okay, so let's take this one at a time. Here's the graph they give you. Speed, velocity, meters per second, versus time in seconds. Okay, and it looks like this, 0, 1, and it starts right here. What's this value that it starts at?
1.6.
Did I get in the way?
Starts right here at 1.6. And then it descends down here to 0.5. And this is at 2, and this is at 3.5. Okay? All right, it says, what's the acceleration of the cart at 3 seconds? Okay, 3 seconds is right here. Go up and over. Is that what our acceleration is?
We want the slope.
Yeah, we want this.
Ah, okay. Kinematics dictates that if we have a velocity versus time graph, to find acceleration, we find the slope. So you got to find the slope right there. Well, the slope is the same from here to here, right? So you can use that entire thing. Now, let me give you a couple words of caution. If it says that you need to find the acceleration, and the acceleration equals the slope of this graph, it says calculate. Calculate means show your work. Okay, so you need to show how you found your slope. Don't just put a number down. You won't get full credit. I know it's an easy thing for you to find. Slope is pretty straightforward. But show some work. At least say it's rise over run or something. Delta V over delta T or something. Or say it's the slope. You need to show something. And when they say calculate, show your numbers that you're using. Okay?
0.73.
Okay, if you put 0.73, you missed some points.
Yeah, it's negative.
Number 1's negative. Number 2 is
Meters per second.
Meters per second squared.
meters per second squared. You got to put our units on there. Okay, so don't forget. Did you put it on there?
Teach me how to tell. Teach me.
All right. Next question is, calculate the distance traveled by the second cart during the 5-second interval from 0 to 5 seconds. Okay, how do I figure out how far this darn thing went?
Area.
Okay, area under the graph. Okay, all the way out here to 5 seconds. I've got to find area. Oh, goodness, I've got a crazy area.
I just divided into 2 rectangles and a triangle.
Yeah, that's what I did. I picked this triangle. I picked this triangle. And then I picked this. I'm sorry, I picked this rectangle.
Wow.
And this triangle. Sorry. All right? Yeah, this triangle, this rectangle. Or the opposite way, whichever. Okay, what do we get?
5.25, so 5.53 if you estimate it.
Okay, this area is about 5.5 what? Meters. Now wait a minute. What if our cart had done this? What if our cart had done this, and then this, and then that?
You have that negative area.
It's the area.
You have to,
I'd have a positive area here, and I'd have a negative area here, and I'd have to have the positive and the negative added together, right? Okay.
Oh, let's see.
Okay, so don't forget, if it goes below the axis, it's a negative velocity, therefore it'll have a negative displacement, right?
Ruin.
Yes.
So do you give that too?
Yeah.
She's really.
Good job.
Yeah.
Okay, state whether the ramp goes up or down. State whether the ramp goes up or down. The ramp goes. All right.
up. It goes up.
All right, hang on. You need to stand by this table.
That goes
This
down.
table needs to answer. State whether the ramp goes up or down. How do you know? Because why? Because it slows down. So the ramp goes up. But how do we figure out how high the ramp goes?
Area under that specific part.
Really? Because what's this area? Is this area
That's
the
distance.
vertical?
That's this.
That's how far the cart goes, right?
That's including. It's.
Ooh, how about the cart starts off down here. It goes, we said it goes up a ramp, ends up here.
Yeah, that's right.
So what kind of energy do we start with?
Kinetic.
Kinetic. What kind of energy do we end with?
Potent.
Oh, be careful.
Well, we can't assume because we don't know if it's stopping or not. It just says
We do know whether it's stopped or not.
It's still going. It hasn't stopped.
It doesn't say.
Nice pass.
0.5 meters
So
per
it's-
second.
Say that again.
Yeah, that's
Say that again.
Why is he taller, Mr. Bruin?
I need to be taller. All right. Hey.
No, leave it on there. Hey.
Okay.
I just need to stop.
All right. Listen. Hey. What kind of energy does it have at the top of the ramp? How do we know it still has kinetic?
Because it's
But it's still moving. Plus potential. Ooh, this is a pretty tough problem. This problem just keeps going on and on and on. Okay, kinetic. And then later we have kinetic and potential. All right, so figure out how high that ramp goes. Let's go to problem 194. With really masculine stick figure there, kicking ball over fence.
Oh,
That's right. Back when I was a little bit thinner. Problem 194.
Back in the day.
Yeah, back in the day.
But still bald.
Oh, you're great job.
That's some rough stuff right there.
That's right. Don't mess with me. Okay, problem 194. It says a ball of mass 0.5 kilogram initially at rest is kicked directed towards the fence 32 meters away as shown. The velocity of the ball as it leaves the kicker's foot is 20 meters per second at an angle of 37 degrees.
For us. Are you kidding me?
Yes, the trig is on there. Actually, it's always on there because that's the same trig that shows up on your constant sheet anyway. The top of the fence is 2.5 meters high. The kicker's foot is in contact with the ball for 0.05 seconds.
Why do we need to know that? That's
Okay.
Force sometimes you can calculate it when you have to change it.
Yeah. Okay. The key thing is if they're talking about a force and they're telling you about a time, what are they giving you? They're giving you the change in momentum or the impulse, right? Very nice. The ball hits nothing while in flight and air resistance is negligible. Calculate the magnitude of the average net force exerted on the ball during the kick. That's question A. Question B is determine the time it takes the ball to reach the plane of the fence. Question C is will the ball hit the fence? Yes or no? If it goes below, how far below, or where does it hit the fence? How far below the top does it hit the fence? If it goes above, how high above the fence does it go?
or does it even hit? hit the floor.
This is trajectories too.
Yes. So we got trajectoriness.
Trajectoriness.
All right, so go. Everybody work.
If you just do two, that's
All right, before we get too far into this trajectory problem, the young gentlemen at the back of the room have figured out how high the ramp is by doing conservation of energy. Okay, I will tell you a couple things.
No, that, yeah, what's that?
Meters.
That's a Greek symbol for squiggle. Otherwise known as meters, I think. Okay,
wiggle.
there we go. It's got a tail on it.
It's supposed to be meters. That's the answer to meters.
There you go. Nice.
No, now it's more.
Now it looks like.
All right.
Yeah. Molarity.
That's right. It's 0.12 molar.
Okay, what?
Okay. Molarity.
I know.
Okay, just check.
I was just.
Okay, I will tell you one thing here, that you won't get full credit. Well, you might get full credit, but if you want full credit,
Initial
you
equation.
definitely have to have the initial equation. So I would just say energy 1 equals energy 2, and then tell what kind of energy you start with. And you have kinetic over here equaling kinetic plus potential. So this is your side 2, this is your side 1, beginning and ending, right?
Yeah.
Don't forget your equation. Okay, if you want to really make sure that you have the grader love you on the test, and that's what you want the grader to not have any excuse not to give you full credit, right? So you need to make sure you show your equation. I know for a lot of you, you're not used to doing that, you just have to, okay? Write the initial physics, write the next equation, and then if you want to start plugging stuff in, that's fine, okay? And also, if you had some strange thing like, remember we had the problem where we had like the kid swinging from the end of the rope like this, and we had to figure out what the original height was?
Yeah, and he's tying himself through his head.
That's correct.
No,
Like
he's
wearing,
committing
he's
suicide.
clamping it right in.
He's plugging in.
No, he's not dead. I'm not dead yet.
His head snaps off.
All right.
Until he stops.
That's right. All right, so here's the deal. In this particular problem, it's conservation of energy as well, where you have gravitational turns into kinetic over here. But the thing here is mgh 1/2 mv squared. But remember, we had to find that height. And so you need to show them how you found the height in this case, right? Like, how did I find this height? Over here, you didn't have to do that. But in case there's something like that where you have to find, you know, what goes in one of these, you need to show how you did it, okay? All right. So there is our maximum height of the ramp. Our ramp is 0.12 meters high, okay? All right, we're on to our trajectory problem then. Get to work on that trajectory problem, please.
Trajectory problem.
Of the boy kicking the ball. Actually, I shouldn't say a boy. The little Mr. Bruin stick figure, because it's bald. Yeah, hey everybody. Trajectory motion. You're launching on an angle, correct?
Yeah.
Very first thing you do anytime you're launching on an angle is what? Yes, split it into components.
Yeah, there you go.
20 meters per second. Hey, everybody, when you see the magical 37 degrees, what kind of triangle?
3, 4, 5.
It's a 3, 4, 5. This is a 3, 4, 5. So you can either say that this is 20 times the sine of 37, and you can say that this is 20 times the cosine of 37, or you could do this. 20 is the 5 side. Take 20 divided by 5, which is? 4. What's 4 times 4? 16. What's 4 times 3? 12. Okay? So you can do that trick too and ratio up your triangle, your 3, 4, 5 if you'd like. If that makes good sense to you and you like that, then do that. If not, then don't worry about it. Just use the sine and cosine. Okay, part A says what's the average force of the person's foot on the ball? Well, the only thing they give us as a clue is they give us the time of contact. And so the only equations we have that include force and time is impulse equals the change in momentum, which for us is the change in mv, or the m times the change in v, which is mv final minus v initial. Our initial velocity of the ball is 0. So it's going to be force times time equals my mv final in this case. We know what m is, we know what v is, we know what t is, we can find our force. Our force turns out to be 200 newtons? Yeah, 200 newtons. Okay, with the information given, knowing that the velocity, the mass was half of a kilogram, the velocity was 20 meters per second, and the time of contact was 0.05 seconds. So our force was 200 newtons. All right. Now determine the time it takes the ball to reach the fence. Okay, here's the deal. Our fence is way down here. Our fence is 32 meters away. Okay, the time to reach the fence. I can find time in either the y direction or the x direction. Which one is best to use this time? Yx. Yeah, because I know the x distance and I know the x velocity, and there's no acceleration. So this just equals the x velocity times time, right? And I know that that's 16. So my time is 2 seconds on the nose. They were nice to us. Then ask, how high is the ball, above or below the top of the fence? Okay? How high above or below? That's a y question, right? So we're looking for the y location. Y equals y naught plus v naught t plus 1/2 gt squared. Okay, very important.
Why not?
Y naught is 0.
Why not?
We know that is 12 times time of 2 seconds.
Are we doing up to that?
Hey, I'm glad you said that. All right, I made a mistake. What's my mistake?
One has to be negative.
Yeah, which way did I determine is positive? Up. So this has got to be a negative 9.8. So that's going to be a negative 1/2 of 9.8. If you do that, you get like 4.4. So is our answer 4.4?
No.
Uh-oh, no. Oh, because 4.4 is up here, so the ball goes like this, and they want to know this distance. So you got to subtract off the height of the fence.
So 1.9.
Yeah, it turns out to be 1.9. Oops, 1.9, sorry. Over the top of the fence, because the fence is 2.5 meters tall. Okay, we are running out of time. Couple of quick things, everybody. You need to study for this test.
Yeah.
This test will be about 70 minutes. It's going to be a pretty strenuous test. You need to know your stuff. You need to remember that the tests are a little bit comprehensive. So I will tell you of those 24. Oh no, not on this one. It's the next test where I've got some thermal questions on it to keep you honest.
Oh wait, next.
Not this one. Next one.
We'll forget about it. Just
All right. You got enough to worry about on this one. Now everybody, I will tell you. Shh. 3 response questions. There's going to be kinematics on it. One of them is going to be trajectory. There's going to be momentum on it. One of them is going to be 2-dimensional. So you need to make sure you know your 2-dimensional momentum collisions. You see this problem right here? The one where the ball hits the other one on the table?
Yeah.
That's like that.
The second part of it, where it goes off at an angle, and like the one we did in e-homework, you need to You need to make sure you understand that. I'm going to post the key outside, okay?
At what time? During
I'm going to post the key right now.